Hey everyone, welcome back to the channel. I am Rachit Kakad, CSE student who loves solving problems. And today we are taking out one of the most asked advanced LeetCode hard problems out here, which is median of two sorted arrays. Let's go on it. Okay, so this is the one. Most people look at it and go, but it's so easy to do. Just merge the arrays and find the middle. And yeah, that's how it works. But the problem is literally the problem tells us to have the solution which has to run in the order of log of m plus n time. So merging out is not our in syllabus, and that's where the things get interesting. So what we have to do is we have got two sorted arrays, nums1 and nums2. We just need to find the middle of the both of them, but combined. The whole problem is this. Just to give you a quick reminder, if you go on the Google and search what is median, let me give you here. Median means if you lined up all the numbers in order, then the middle value you get is the median. In case of odd numbers of elements, it's just the middle one. And in even numbers, you take two middle ones and average them. That's how simple. Now, let's look at the examples which LeetCode has given to us. First one is nums1 is 1 comma 3 and nums2 is 2. Combined 1 comma 2 comma 3. That's how three elements we get. The middle one is the 2, so the answer is 2. The second example, we have the nums1 is 1 comma 2 and nums2 is 3 4. Combined, that's 1 2 3 4. Four elements, so 2 in the middle, 2 and 3. Average is 2.5. That's our answer. Cool. Now, how do we do this in log time without actually merging? That's the approach I am telling you. So, what's the key idea? The, the key idea is instead of merging, we find a partition. We cut the nums1 at some index I and nums2 at some index j, such that everything on the left of the both curves is smaller than everything on the right. If we can find that perfect cut, we can directly calculate the median from just the four boundary values. We apply binary search on the smaller array, pick up a midpoint I in nums1, calculate j, so both left halves together have the right numbers of elements. Then we have to check, is the left side of the nums1 less than or equal to the right side of num2 and vice versa? If yes, then we found our partition. If not, we have to shift left or right and try again. That's how a classic binary search works. Let me write this out for you in C++. Here. So you might be thinking, why we wrote this line? We always want the binary search on the smaller array because the smaller array, the fewer iteration we do. If num1 is the bigger one, then we have to smap and call the function again and again. Doesn't change this answer, but we have to make our binary search faster. Then let's like next thing. Low and high are our binary search boundaries. Notice I is m, not my m minus 1. That's because the partition can sit anywhere from 0 to m, including completely at the end. We are not indexing into array here. We are choosing a cut point only. This is how many elements we want on the left side in total across both array combines. This one handles the odd case. If the total is odd, we have the left side to have one extra element so that median sits at the right at the boundary. So we have to write here I, because the j would be high minus 1, half minus 1, sorry. I is our partition in nums1, standard binary search, midpoint, and j is half minus 1 because if we want half elements on left, then I of them should be of nums1 and remaining j have to come from nums2. That's what I mean, right? Sorry for the mistake. We are having just copying these two lines because we have to just change the values on them. Here L2, I should be replaced by j, and it means nums2 and j of nums1. Here we would have j and here j are 2. The four values are four boundaries of our partitions. L1 is the last element on the left side of nums1, R1 is the first element on right, same for nums2. But why int mean and max? If I is 0, there is nothing on the left on nums1. So we pretend it's negative infinity so that we never blocks a valid partition. If I is m, there is nothing on the right, so we use positive infinity. Same logic for nums2 uh, of j. It's just a safe boundary handling. Now, writing over further. This is the condition that tells us didn't we find the right partition. L1 less than or equal to R2 means left side of nums1 doesn't spill into right side of nums2. L2 greater than L1 means the left side of the nums2 doesn't spill into right side of the nums1. Both have to be true. If they are, everything on left is smaller than everything on the right. Perfect partition. Just adding a bracket so that it gets prioritized. If L1 is greater than L2, then R2, our cut in nums1 is too far, right? We are putting too many big elements on left side from nums1. So we move I left to shrink I. Otherwise, L2 would be greater than R1. So our cut is too far in left. We need more elements from nums1 on left side. So we move low right to increase I. That's it. The standard binary search adjustment. All right. That's my submission. So let's hit submit button. Accepted. Time complexity order of log of minimum of mn. Space is order of constant clean solution. That's median of two sorted arrays. The whole trick is don't merge, just do a partition. And once you understand why each line exists, the solution actually makes total sense. If this helped you, drop a like. If it does really help the channel to grow and to make such videos, comment below which problem you want to see next. See you next time. Till then, thank you.